Okay, so first I would like to mention that in fact, taking into account very interesting talks in this session on representation theory, maybe it would be more suitable if I was speaking about representation theory because I'm working on that as well. But maybe we can save it for the next year's conference then. Okay, so my talk today will focus on topological dynamics of operators. And just some introductory words. First, the main concepts in the topological dynamics are, for instance, hypercyclicity and supercyclicity. And then later, people studied Furstenberg transitivity as a generalization of hypercyclicity and topological transitivity, for instance. And then quite recently in my paper in Philomath in Serbia, I introduced the notion of Furstenberg semi-transitivity, which is supposed to generalize in the context of Furstenberg dynamics supercyclicity. So you have the generalization of hypercyclicity in the context of Furstenberg dynamics already, and it is called Furstenberg transitivity. And this is just, the main idea was just to extend then supercyclicity in the context of more general Furstenberg dynamics. And then in my paper in Philomath, I studied for the special case of generalized weighted bilateral shifts. But quite recently, my accepted paper, which will be published in these days, I expect, in Annals of Functional Analysis, generalized my previous results from the case of generalized weighted shifts to the case of more abstract operators on more general Banach algebras and Banach bimodulus. And this is what I will talk about now. Okay, so first we need a definition. What is this Furstenberg semi-transitivity? We let S be a set, and then this F is supposed to be a family of subsets of S, arbitrary family of subsets of S, and then we have some families of operators indexed over this set S, families of bounding linear operators on a Banach space X. And then we say that these families are disjoint Furstenberg semi-transitive, or shortly DF semi-transitive, if for every collection of non-empty open subsets OV1 up to Vn of X, there exists some element belonging to this family of subsets, so some subset F belonging to this family, such that for all t in F, we can find some positive scalar lambda t, such that this intersection is non-empty. And I want to compare it with the classical Furstenberg transitivity. In the classical Furstenberg transitivity, you don't assume existence of such scalars, but all these scalars are equal to 1. So if you remove these lambda t's and require that each lambda t is 1, then it reduces to the classical Furstenberg, disjoint Furstenberg transitivity. But in the same way as supercyclicity arises from hypercyclicity when you consider more general scalars and not just scalar 1, also here this is what is done. So we extend the notion of Furstenberg transitivity in this way here. And now we need this general setup. So we will study these dynamics on general Banach algebras, as I said, but still we will need some assumptions on these Banach algebras. Okay, so A is supposed to be a non-unital Banach algebra such that A is a left ideal in unital normed algebra A1. But we will consider the general case where the norm of A is not necessarily the same as the norm on A1. But we will require another thing. We will require that this holds. The condition E, this means that for all A in B in A1, this inequality is satisfied. And then we shall assume that we have a net in A satisfying that given any open subset O of A and any X in O, we can find some element of this net such that this to the power 3 times X is in O as well. So something like approximate unit, but more general because we require here power 3. And this is called the condition P. And we also need the families of isometric algebra isomorphisms of A1 such that they are also restricted over this set S, and such that the restriction of this each of these algebra isomorphism to A is an algebra isomorphism of A. So it maps A onto itself and is an isometry. And then we will assume that this system is disjoint aperiodic with respect to this approximate unit P alpha. What does it mean? This means that for each fixed P alpha and every subset H which is an element of this family F, we can find some F a subset of H such that F also belongs to this Furstenberg family, and such that these relations hold for all RL in this finite set 1 up to n, and with R different from L, and for all T in F. So we require the existence of such subset F belonging to this family F, such that this holds for all T in F, and these R and L. And then another condition which we will assume is so-called the condition R. This means that these inequalities hold for each index alpha from this index set of the respective approximate unit which I mentioned above, and all T in S and RL in 1 up to n. And now we will deal with operators of this kind, which are a composition of you first apply this isometric isomorphism, and then you multiply from the left by an element. So exactly speaking, we do the following. We take families of elements in A1, and then we construct these operators. And due to the condition E, let us recall the condition E. This was the condition E. Due to this condition, we have that this operator is a bounded linear operator on A. And now we are able to provide characterization of DF semi-transitivity for such operators. Just before saying that, I want to say that when we choose these elements here, the easiest case is when they are invertible. But if they are not invertible, then we need one weaker assumption, is that for each index alpha from this index set of the approximate unit, then each BTL should have so-called alpha inverse, denoted in this way. And this means that this inverse, alpha inverse belongs to A1, satisfying these equalities for every A in A in this fixed alpha. So you see that it is almost like inverse, but it's still not inverse, because we require these equalities only for a fixed P alpha here. So when you consider the elements of the form A times P alpha, then you want that this holds. And also you will require that BTL does not have any zero divisors. So if you have BTL A equals 0, then necessarily A must be a 0. So this construction is needed because in the concrete case of weighted shifts, you can consider the weighted shifts where each weight is non-zero, but weights may converge to 0 when n goes towards infinity, and then they will not have in the respective Banach algebra the exact inverse, but they will have such alpha inverse. I will explain later how it can be interpreted in this concrete case of weighted shifts. But let us first give the characterization of DF semi-transitivity of these operators. So these operators are DF semi-transitive if and only if for each fixed P alpha from this approximate unit and every epsilon greater than 0, we are supposed to be able to find some F belonging to this Furstenberg family and some families in A indexed over this F, such that this inequalities hold, and this inequality holds for all t in F and every RL in this finite set, and moreover, for each distinct RL in this set and every t in F, this inequality should hold. And then we can here this theorem is maybe difficult to apply, not in all examples, but in some examples it can be complicated to apply because we require the existence of these families. So here we have some sufficient conditions which can be sometimes more useful in concrete examples. And here we let now this be the family of all infinite subsets of the natural numbers, this Furstenberg family. So it is now a concrete Furstenberg family. And then we require that if we assume that if there exist dense subsets A0, beta 1 and up to beta n of A, and a strictly increasing sequence of natural numbers nk, such that for each SL in this finite set, every fixed alpha, and all alpha is now again from this index set of the approximate unit, and all x in A0 and is in beta s, for any s in this set here, this limit should be 0 as k goes towards infinity. And in addition, for each distinct SL in this set, we require that this limit is 0 when k goes towards infinity. And then, if these conditions hold, then these families will be DF semi-transitive. So this is something which is a typical tool in the dynamics, that you check whether your conditions are satisfied in terms of the existence of some suitable dense subsets. So once you find such dense subsets, then they will guarantee you DF semi-transitivity of these families of operators. And we will see that in some cases these conditions are more useful than the conditions the above here, but in some other cases we will directly apply this theory. And now I am, as I promised, coming to the concrete example of generalized weighted shifts. But we are not going to study the classical weighted shifts on little l2, but we are going to study something more generalized weighted shifts on L2 of C, where L2 of C is the standard right Hilbert module over a C-star algebra denoted C. Okay, so just to fix the notation for a separable Hilbert space H, BH is as usual a space of all bounded linear operators on H, and C is the C-star algebra of compact operators on H. So we study the concrete C-star algebra C, and then we will take a fixed orthonormal basis for H indexed over Z. This is for practical things, because we are dealing with shifts, so for practical things we indexed over Z and not over N. And for this orthonormal basis EJ, for each natural number m in N, we let Pm be the orthogonal projection onto the span of these elements from E minus m up to Em. And as I said, L2 of C is the standard Hilbert module over C, and in fact, since this is not an arbitrary Hilbert module, but exactly this standard Hilbert module L2 of C, in fact, it is a non-unital Banach algebra. How is that constructed? Well, you can define the multiplication of these sequences simply by pointwise multiplication. Of course, we need to check that this new sequence belongs to L2 of C, but it follows from these inequalities in the C-star algebra. So note that these inequalities, this is not scalar inequalities, but inequalities in terms speaking of the cone of positive elements in the C-star algebra. So those are all operators. And just to remind, this L2 of C, the norm on L2 C is the norm of the sum of this ij star ij. So it is not the sum of the norms, but it is the norm of this sum, and this sum is supposed to be convergent in the C-star algebra of C. just to remind the definition of the standard module. So now we have seen that this is a Banach algebra, and we need to check that other conditions which we speak above are satisfied also in this case. Okay, so what should be the approximate unit in this case? We let this element in L2C be defined in this way. The ith coordinate of this element is simply this projection orthogonal PM. If I lies between these minus j and j, where j is any natural number n, and it is 0 else. And then I can check that this is indeed a left approximate unit for this module. And now, since this is a non-unital Banach algebra, we let A be L2 of C. But what should be A1 in this case? Well, A1 in this case, we let this be all the sequences whose components are bounded linear operators on H, which are uniformly bounded in the norm. And this A1 can be equipped then with the supremum norm, because now those are uniformly bounded in the norm sequences. And easily it is checked that this is a unital Banach algebra, and that multiplication is also defined component-wise. But now you see the reason why I didn't want to study the case when A1 has the same norm as A, so that the norm on A1 is extension of the norm on A, because here you see that we are dealing with the different norm, and this is more useful for our purposes. Of course, every non-unital Banach algebra can be somehow embedded in a unital Banach algebra and the norm extension, but here this is more suitable to study the case when A is ideal, left ideal in a unital Banach algebra having another norm, because this can be adopted for the very concrete cases of shifts and so on. Okay, so now we have checked some of these conditions. Now we need the setup of these algebra isomorphisms. How are they defined? Well, I take some numbers R1 up to Rn in n, which are satisfy these inequalities, and we let U1 up to Un be unitary operators on H, and then for each n in n and s in 1 up to n, I define this map here in this way here. So it acts on this sequence, it gives me this sequence here. What is this? This is actually first the forward shift by Rs plus n components, and also it is a left and right multiplication by this unitary. So it is simply a generalization of the classical forward shift by Rsn components. And it acts on A1, but one can check that the restriction of this to A is also an algebraic isometric isomorphism. And we will study now the case when Furstenberg family is the family of subsets of n, which is finitely invariant. This means that for every n in n and f in f, it holds that if you remove from f this finite set, then this new set still belongs to f. And one can check that this is a disjoint aperiodic system with respect to this left approximate unit, and also the condition R is satisfied in this case. I can just quickly remind what was the condition R. Let us just go above here. This is the condition R. So these inequalities in the norms, this by some calculations can easily be checked. And then we also need these elements B and L. How do we construct them? Well, we take some families of operators in BH which are uniformly bounded in norm, and such that each of these operators has a bounded inverse. And then we define B and L in A1 in this way here. So ith coordinate of B and L is given in this way here. And the condition C is satisfied because this operator is invertible. Recall that condition C was that B and L has no zero divisors. And then we now, what is now this operator? Now, due to the special choice of phi and b, this operator is actually a generalized weighted bilateral shift. Then with weights, generalized bilateral weighted shift with weights v and l. And the only difference is that it will also multiply from the right by these unitary operators, but in fact, it acts on L2C as a generalized weighted bilateral shift with these weights V and L. And then it can be checked how this inverse, alpha inverse, looks like. Alpha in our case is now Jm, a pair of these natural numbers, because our approximate unit in this concrete case was indexed by these pairs of natural numbers. And now we can provide a characterization of generalized weighted bilateral shift on the standard module. It is the equivalent conditions are expressed as follows. For every Jm in n and epsilon greater than 0, there exists some f in this Furstenberg family, such that for each j in z with j, little j lying between this great capital minus j and j, we can find some families of compact operators on H indexed over this set F, such that these inequalities are satisfied for all n in F and Ls in this finite set, and in addition for each distinct SL in 1 up to n and all n in F, this inequality is satisfied. And exactly in this concrete case, it can be sometimes hard to adopt this theory for constructing concrete examples, and this is the reason why I introduced above this alternative corollary with some sufficient conditions, because if you interpret that corollary in this concrete case, you get something like this. Let me just read it. So it is that for each j in Z, there exist dense subsets H0j, H1j up to Hnj of H, and strictly increasing sequence of the natural numbers, such that for each SL in 1 up to n, and every xj in H0j and isj in hsj with s from 1 up to n, this limit holds when k goes towards infinity, and moreover for each distinct SL in this set and every isj in hsj, this limit holds when k goes towards infinity. If all these conditions are satisfied, then our operators are DF semi-transitive. So now we managed to express the conditions in terms of the existence of dense subsets of H where this is satisfied. And this is easily for the construction of the suitable the operators W. And I have my examples in this paper, which will be published soon. For the interested readers, I can send, interested listeners, I can send the paper itself containing the concrete examples, but there are concrete examples. But this is not the only case. We can study also some other generalized shifts on some other standard Hilbert modules, and we can also study it on some other Banach bimodules. I probably do not have time to go through all this, but I want to conclude this talk saying that the purpose of studying this in an axiomatic way of Banach algebras and general Banach bimodules is because then it will cover several situations. Otherwise, we would need to study all of these concrete situations in itself. It is possible to do, but when you have a general theory, then you can just, the remaining work is just to interpret this general theory in this concrete context to get some concrete conditions and thus concrete examples. So I believe that my time is up now. Am I right?
Yes, Stefan, thank you very much for your talk.